In many hydraulic applications, it's necessary to control the direction in which fluid flows. To do this, we use a directional control valve. From an earlier lesson, we know that directional control valves work by shifting an internal movable part. We will refer to this movable part as a spool, though it could be a poppet or a disc as well. This movable spool opens or closes various passages or ports in the valve. In this lesson, we are going to take a look at different kinds of directional control valves, and we will discuss various techniques used to shift the spool. In addition, we will look at a special kind of directional control valve that controls direction and flow rate at the same time. Let's begin by looking at the different kinds of directional control valves found in many industrial systems. These valves are designated as two-way, three-way, or four-way valves, depending on the number of ports they have. A two-way directional control valve is generally used to connect or isolate parts of hydraulic systems. With the spool in one position, the valve passage is blocked and fluid cannot pass. When the spool is shifted to the other position, the passage is opened and the valve becomes passing. Occasionally, three-way directional control valves are used. These valves have three ports, one going to pump, another to tank, and the third to an actuator. In most cases, when a three-way valve is required, a four-way valve is used and one of its ports will be plugged. The most commonly used directional control valve is the four-way valve. Its four ports can be interconnected in various ways, depending on the type of spool used inside the valve. Notice that all the ports on this directional control valve are located on the bottom of the valve. This is done to make servicing and installation easier and more efficient. The body of the valve is bolted to a precision-made subplate, and the system piping is connected to the subplate. If the valve must be removed for service, it is simply unbolted from the subplate. The lines don't have to be disturbed. Combinations of subplates called manifolds are sometimes used when several valves are mounted side by side. This reduces space requirements and allows several valves to be controlled from a single compact operator station. Some directional control valves only have two positions. The spool can be shifted to one extreme end of its travel or to the other. For example, this four-way directional control valve opens a passage from the pump to port A and from port B to the tank when the spool is shifted all the way in this direction. And it opens a passage from the pump to port B and from port A to the tank when the spool is shifted all the way in the other direction. However, many valves have a third or middle position. What they do in this middle position, or center condition as it's called, depends on the kind of spool that is used. While many different spools are available, the four most common are the open center, closed center, tandem center, and float center. Let's start with the open center spool. Centering the spool connects all the passages together. Flow returns to tank at a low pressure, and the actuator is free to move in either direction. However, once an open-centered spool is centered, other actuators in the same system will not operate because system flow is being returned to tank. A closed center spool, on the other hand, blocks all four ports when the spool is centered. This permits actuators to operate independently of each other, and it also allows cylinders to be stopped in mid-stroke. However, a cylinder rod stopped by a closed center spool will gradually drift out if the valve is left in its center condition for more than 2 or 3 minutes. This happens because fluid leaks past the spool, building up pressure at both ends of the cylinder. Since the cap side of the piston has more area exposed to pressure than the rod side, the rod creeps out. A closed center spool also requires the system to generate a lot of heat, even when no work is being done. As long as the spool remains centered, flow from pump to tank is blocked, so pressure continues to rise until the relief valve is forced open. A tandem center spool can stop cylinders in mid-stroke and reduce power consumption by dumping the pump directly back to tank. This is possible because a passage drilled through the spool connects the pump to tank. However, the passage does restrict flow and raise pressure. So if several tandem valves are operated in series, the cumulative effect may force a system to produce a lot of heat even while idling. The fourth center condition is the float center or motor spool. It connects both sides of the cylinder or motor to tank, allowing the actuator to float or move freely whenever the valve is centered. If the actuator must be stopped for some reason, a pilot-operated check valve can be used. In this example, the cylinder will not continue to stroke until pressure on the A side of the cylinder rises high enough to unseat the check valve. Centering a float spool also blocks the pump passage. This means several different actuators can be operated from the same power source because full pump flow and pressure are diverted elsewhere in the system when any one spool is centered. Now, even when a four-way directional control valve has only two positions, it may still have what's called a crossover condition, and it may affect the operation of the system. In this symbol, the dotted lines indicate that although the valve has only two positions, there is a third position for an instant as the spool shifts from one end of its travel to the other. In this example, the spool has a closed center crossover condition. During a shift from one extreme position to the other, pressure will drop very little. In some applications, however, a slight drop in pressure may be desirable. For example, if a heavy load must be reversed, an open center crossover condition may be used to minimize shock as the spool shifts. Now, we've seen what happens when valve spools are shifted, but we also need to understand how they are shifted. All directional control valves require an external force to shift the spool. The force comes from the valve actuator, which may be manual, mechanical, hydraulic, pneumatic, or electric. Manual actuation is simply when human energy pushes a button, shifts a lever, or steps on a foot pedal. Manual actuation is used on things like fork trucks, which require an operator to direct the movement or to sequence the operation. Mechanical actuation is usually accomplished with a cam, which is simply a valve with a roller or ball on the end of an extension of the spool. The roller or ball contacts some part of a machine member, like this cylinder rod extension, which moves it in and out. Mechanical actuation is commonly used when valve shifting must occur as the machine reaches a specific position. Either air pressure, pneumatics, or fluid pressure, hydraulics, may also be used to move the spool. Usually, a separate, smaller valve provides the pneumatic or hydraulic pressure used to actuate the larger valve. This is called pilot operation. Shifting the spool can also be done electrically with solenoids. Solenoids are electromechanical devices which convert electrical energy into linear mechanical energy. Two types of solenoids are most often used to shift industrial hydraulic valves. They are the air gap type and the wet armature type. An air gap solenoid consists of a wire coil surrounded on three sides by a C-shaped iron frame. Both frame and coil are often encapsulated in plastic for protection. An iron rod, or plunger as it's called, is inserted through the hole in the coil. When voltage is applied to the coil, a strong inrush current develops a powerful magnetic field, drawing the plunger into the coil and moving a pushpin. The pushpin moves or shifts the valve spool. When the spool moves, the plunger seats in the coil, and current drops to a much lower holding level, just high enough to hold the spool in place. If the plunger fails to seat for any reason, current will remain at the higher inrush level, and the coil will eventually burn out. Wet armature solenoids work similarly. However, the solenoid tube is screwed into the valve body, and fluid from the system surrounds the plunger. When voltage is applied, high inrush current creates a strong magnetic field that pushes the plunger against the pushpin. As with an air-gap solenoid, current drops from the higher inrush level to the lower holding level as the plunger seats and shifts the spool. Solenoids sometimes fail, and when they do, it's usually because of blockage of the spool, because of high temperatures around the solenoid, or because of low voltage. Blockage usually occurs when the spool cannot move freely. Often this is due to some kind of contamination, silt in the valve or varnish on the spool, for example. Sometimes spools will stick because the valves are improperly mounted on slightly warped or damaged subplates. If the spool does not move freely, the plunger in the solenoid will be unable to seat properly. The high inrush current will not drop to the lower holding level, and the solenoid will eventually burn out. If air temperature around the solenoid is too high, the coil may not be able to dissipate the heat it generates, even when current is at the lower holding level. The insulation on the coil windings may age rapidly, and the coil will short out. Low voltage may also cause solenoids to fail. At low voltages, the coil may not develop enough magnetic pull to seat the plunger and move the spool as quickly as it should. Until the plunger does seat properly, inrush current will continue to be high. Again, the coil may get so hot it will burn through its insulation and short out. A solenoid generates a relatively small force, so it can be used only with relatively small valves. Typically, these are half-inch valves or smaller, handling a maximum of 20 gallons per minute. When larger size valves are to be electrically actuated, they are usually piggybacked by a smaller valve. The smaller valve, mounted directly on the larger valve, is operated with solenoids. The hydraulic output of the smaller valve operates the larger valve. Valves like this are called solenoid-controlled, pilot-operated directional control valves. Control of the pilot valve is by solenoid, and movement of the main valve spool is by hydraulic pressure from the pilot valve. No matter what method is used to actuate the valve, the spool may have to be held in position. One method of holding the spool in place uses detents, in which a spring-loaded ball rides in and out of notches in the spool. Thrust applied to the end of the spool forces it to move beneath the ball. As long as there is no end thrust, for example if the solenoids are de-energized, the ball remains seated in the notch and holds the spool in position. Spools can also be held in position with springs. For example, the closed center spool in this solenoid-operated valve would vibrate out of position without the springs at either end. The springs hold the spool in place whenever the solenoids are de-energized. Spools can also be pressure-centered. Usually this is done for larger pilot-operated valves and with valves subjected to high rates of flow. For example, the main valve spool in this pilot-operated valve requires a great deal of force to move, so it is centered by pressure produced by the pilot valve. The pilot valve can be spring-centered because it's smaller and lighter, and because flow through it is not enough to move the spool off-center. Pilot operation of directional control valves usually requires that special attention be paid to pilot pressures. Pilot pressures in a valve often vary, and pressures that are too high or too low can affect the operation of the valve as well as the system in which it works. Hydraulic shock may occur in pilot-operated valves just as it does in those which are directly operated. A common way to reduce the effects of hydraulic shock is to equip the valve with a choke control. Although this will not completely eliminate the shock, it will reduce shock by slowing down the spool as it shifts. A choke consists of two needle-type flow control valves and two check valves installed in the pilot passages between the pilot valve and the larger directional valve it controls. As the spool shifts in one direction, a needle valve meters flow out of the pilot spring chamber of the larger directional valve. the other needle valve is bypassed. When the spool shifts in the other direction, the other needle valve meters flow, and the first needle valve is bypassed. Adjusting the needle valves varies the flow and controls the speed at which the spool shifts. Sometimes pilot pressure can fall too low to shift the main valve, or pressure can get too high and cause the valve to shift at the wrong time. For example, if the spool of the main valve is returning to tank while centered, system pressure may be too low to supply enough pilot pressure to shift the main valve, even if the pilot valve does shift. To make sure there is enough pressure to shift the main valve, a back pressure check valve can be used. The check valve is biased with a spring strong enough to prevent fluid from returning to tank unless there is enough pressure to shift the main valve. Sometimes surges of flow into the tank line can cause erratic operation of pilot-operated valves. This can occur when large flows are returned to tank through an internal drain. Pressure from other parts of the system which use the same tank line can briefly back up into the internal pilot drain, interfering with normal operation. Changing the pilot drain from internal to external will solve the problem. This will provide the pilot valve with its